our project demonstration for Whisper, which is our 1.58-bit conformer model that is used for on-device speech-to-text. The goal or the problem, high-level problem that we are solving is that studio quality transcription should be available in your pocket. We want speech-to-text models that is instant, private, and always accessible without relying on the cloud. But today there is a fundamental trade-off between the two. Large models are hosted on cloud by big players where there is no data privacy insurance, and they have a very high accuracy. They are good models, but they require a lot of compute. Not everyone can run them. While on-device models have always been small, they run very well. All your data is private, but the performance is not good. We want to bridge this gap in our language model or conformer model setup. There were two motivating works that led to a 1.58-bit conformer model. That is, we started by reading out the era of 1-bit language models, which is a paper by Microsoft Research that tells that if your weights are +1, -1, and 0 for all your projection layers and multi-head retention, you can still achieve very good results while reducing the number of total parameter model size. This inspired us to see what if we could train such a model for ASR tasks, and lo and behold, we found towards 1-bit ASR, which does exactly that. The biggest issue with towards 1-bit ASR is there is no open source reproduction of this task, and we only have to believe what the model authors and the paper writers have written. We wanted to change the status quo and make sure that we deliver a project that is capable of training any 1-bit ASR model on any type of speech-to-text dataset, and make sure that it is usable by everyone and trainable by everyone. That is the whole motivating factor of our work. Such models, which are meant to be run on small devices, should definitely be trained through open source platforms. So the task at hand is provide a scalable way to train a 1.58-bit conformer and make sure that it works. The expected memory efficiency results and the true efficiency results that we have gained are as follows. We train a 28 million conformer model. If it is trained in full precision, it has around 108 MB model size. If you quantize it into 2-bit, you achieve 45.6 MB, which is a 2.4x reduction in size. And if it's a 1-bit quantized model, you reach 2.5x reduction, which is 43.5 MB. Around 60% of the parameters are quantized, which are the encoder linear layers, and the Q, K, and V layers that we talk about, and other layers such as all layers in the decoder convolutions and batch normalization are left as is. We use torch DDP, where the goal is you replicate the model on multiple GPUs and accumulate the gradient using all reduce and all broadcast. This is done so that we can fit a larger batch size and train a big model on multiple GPUs. Let me walk you through the dataset. We have a train, validation, and test split, and we have engineered a pipeline for downloading 10% of the LibreSpeech ASR corpus. LibreSpeech is a very big dataset, and thus building out an engineering pipeline or data engineering pipeline to generate 10% of the samples was something which is very cool, and it allows you to download a specific subset. We utilize the streaming datasets in Hugging Face and make sure that they work well with our setup. This is how we have converted. This is what the batch looks like during training. We have the features, the feature length, the tokens, and the token lengths. This is the data pipeline flow, which is very important. We take the raw audio, we do feature extraction, we then perform CMV and normalization for zero, mean, and unit variance. So this is the input to the model, and the output on which the model is trained is tokenized transcript. We use the sentence piece tokenizer library by Google to generate a 500 token vocabulary size, and the IDs are shifted by 4 to take care of special tokens. Finally, our method or methodology looks like as follow. We have an encoder with the quantized blocks. You can see on the right how quantization works. It's literally a quantization function where we clip the values between 0, -1, and 1 using W by alpha. There you can see 1-bit, 2-bit, and a stochastic precision model, and we will talk about this in the next slide. So let us see how this entire architecture is trained. We use a final loss, which is computed by the loss on training a 2-bit teacher, and then we train a 1-bit student model and a stochastic precision model. The idea here is the 2-bit teacher training is very efficient, but we also want to use that as a guidance for the 1-bit student and the stochastic precision model. Now one might ask, how do you backpropagate on these quantized weights, which are 1, 0, and -1? How do you change the original weights so that you can get good results? And for that we use something called the straight-through estimator. The straight-through estimator pretends that the quantization is an identity function, and its value is 1 if the backward pass or the weights are within the clip range. For baseline comparison, we have added a image or a table from the original paper that we took inspiration from. Clearly, these baselines are not reproducible, and the entire purpose of our project was to reproduce these baselines. We failed at that part just because we did not have enough compute and memory to train such a model. This was a very ambitious project. How did we verify that this was a data issue? Well, we also took a FP32 model. So you can see that the training loss and validation loss is going down, which is good for us, but the word error rate still remains quite high. Finally, we verified that this was a data number issue and a memory issue rather than an implementation issue by looking at the gradient norms and also training a FP32 full precision model. You can still see that the data is not enough for giving us a smooth validation and training loss, and you can still see the validation word error rate still remains quite high for the full precision model. So finally, let us conclude this project. One, we believe that we should be moving to a much bigger model to truly maintain a good ASR state-of-the-art model. Having a bigger batch size would enable us to have a much truer representation of the real loss and help us diverge easily. Different model sizes and quantization schemes should be tried to figure out the best performing model. And finally, a better estimate rather than using the straight-through estimate could be something that helps in training a much more stable model. We finally believe that we had done and tried out a lot of things, and we would be extending our work even post the semester to make this a cool open source library for training 1.58-bit quantization models.